talk about Newton's law of universal gravitation. Okay, so back in the 1600s, towards the, when would we be talking? Mid to late 1600s, Isaac Newton. Actually, it's kind of an interesting story. He was a genius, obviously. I think, if we're still talking about the guy 400 years later, he's a pretty smart fellow. And he did some pretty important things in terms of physics. One thing that we're kind of probably all aware of are his laws of motion. But he also did a law of universal gravitation. And he also invented calculus, which he actually needed to kind of work on this with. So they kind of go hand in hand. Allegedly, at least what I've heard, he did all this by the time he was 23 years old. So, like, you guys are 18, you got about 5 years to start getting stuff done, okay? All right, so what we're interested in today is this, okay, the law of universal gravitation. Now, there's a famous story about Isaac Newton that he was hanging out in the apple orchard. I'm going to draw this just because it's fun. Okay, so he's hanging out in the apple orchard. And the story goes that he, was looking at some trees, apple trees, and he noticed an apple fall. Some versions of the story, the apple fell right on his head, and he instantly knew about gravity. Actually, what his great leap was that if this story is even partially true, which it may or may not be, I don't know, but in the story, he saw an apple fall, and it was kind of the time of day when the moon was out, and he came to the conclusion that the same laws of physics should apply to the apple and the moon equally, okay? And so basically, Isaac Newton sort of figured out, I guess, that if you were to do something like this here, I'll try to make it make more sense. Like, let's say you have your apple tree here, right? Here it is. And if you, like, let an apple fall straight down. But what if you project the apple outward? Well, the apple will fall a little farther away. What if you project it out even a little bit more? It will fall like that. So first of all, the first thing you notice is that there must be some sort of attractive force, right, between the apple and the center of the earth. But if you continue this logic and you keep launching it farther and farther out, eventually you're going to shoot that apple fast enough in this direction that it will continue to fall, but it'll never actually run into the earth, since the earth is a round ball, right? And so the same force that can make an apple fall then should be able to hold the moon in orbit, assuming the moon is moving. And I mean, it doesn't take too many observational skills to sort of figure out that the moon moves around. And so he tied basically together some laws that were observable on the surface of the earth, two laws up in outer space. Before his time, specifically back in like the Greek days, the universe worked in such a way, or allegedly worked in such a way, that, there was sort of a different physics out in space than there was on Earth. And, why shouldn't there be? It's somewhere else. We're here. We're the center of the universe, and so on. Out in the ether, we don't really know what goes on. So this is sort of a big step for physics, to tie together something like an apple falling to the orbit of the moon around the Earth, right? That's kind of an impressive physical leap, when really before him, those were seen as completely separate, different things, right? I mean, a generation or two before Newton, the moon was traveling on a crystal sphere around the center of the Earth, right? And now it's just hanging in space by some sort of invisible attractive force, which Newton called gravity. So another way to look at something like this, if it helps, is imagine that, this apple gets launched, it's falling towards the Earth, but the Earth is, if you want, moving away from it at the exact same rate that it's falling towards the Earth. So you can, like, put yourself, as eyes on the front of this apple, what you would be seeing, right, is you're kind of always at the exact same distance above the Earth, because as you fall, it tilts away. Essentially, you are in orbit, right? Now, obviously, that can't really, or it's very unlikely that this could happen with an apple. In the atmosphere, you would have drag that would slow you down, and eventually you'd come crash to the Earth. But up above Earth's atmosphere, satellites are essentially doing this. Man-made and natural satellites are doing this all the time. In fact, we're doing this around the sun. The Earth is, if you want, falling towards the sun at the exact same rate that the sphere of the sun is moving away from the Earth, and so on. And this is all through space. So we're going to discuss Newton's law of universal gravitation. So Newton was able to prove a couple of things. One was that the force of gravity is proportional to the two masses that are attracted to each other. Okay? So the force of gravity is proportional to the product of the masses. What does that mean? That means if we have mass 1, we have mass 2, okay, there's going to be some Fg, some gravitational attraction between the two. Okay? If we were to make one of these twice as massive, that would mean that the gravitational force would also be doubled. Okay? If we double both, gravitational attraction moves up to 4 times Fg, etc. Okay, so Newton was able to prove this is true mathematically. How exactly is a little bit beyond me or the scope of this course. And he was also able to sort out this as well. Fg is proportional to 1 over r squared. R squared being the distance between the two objects. So what does that mean? Okay, let's say we have m and m. Let's say we have d. Okay, at this, the attractive force is Fg. If we double d, we make d twice as far. What is that going to do to gravity? Well, 2 squared is 4. It'll drop Fg to 1/4 of what it was before. Okay? And if we were to say triple d, then we'd be at 1/9 of the original gravity, etc. Okay? So this is what Newton was able to prove was true. All right? So far, what we can say is just this from Newton's time. We can say that the force of gravity is proportional to the product of the two masses we're talking about divided by the square of the distance between them. Okay? We cannot say equal yet in Newton's time because there's something missing, and that is a constant to be able to convert something that's in terms of kilograms squared over meters squared into newtons, right? Because Fg has to be in terms of newtons. We need some kind of constant put in here to figure that out, okay? It was later found that there is a constant, and that constant is called G. This is the universal gravitational constant. Not found till probably over 100 years after Newton died by Cavendish. And I think in your little booklets that is covered, okay? But what that allowed you to do is it actually allowed you to now take real measurements to say that the force of gravity in terms of newtons is equal to G, mass 1, mass 2, over the distance between them squared. And the last thing we just want to know is what is the value of G, and I'll just write that down quickly. This is called the universal gravitational constant. Same number all the time.